Okay, we're looking at now a plane of charge, just like a piece of paper, like that, but it's charged up, uniformly charged. We can't talk about rho this time because we don't have a volume. This is an area, a surface area. So there's another way to represent surface area charge, and that's sigma. Sigma is equal to the charge per area. And if we want to know the electric field, a distance y above here, so this is y from here to there is y. Then what I'm going to do is I'm going to put a Gaussian surface that looks like this. It's going to be a cylinder where that point intersects the top of that cylinder. And it's going to come down and intersect our paper. Okay, so it's intersecting the paper there. But then it's going to go further down, all the way down to a point that's just as far away below it. So you see this is the bottom of the Gaussian cylinder. And I want you to know that this distance is also y. It's important that those be the same distance. So can you imagine like a pop can going intersecting here, and there'd be some of it would be down here, chunk, and some of the pop can would be here, chunk. That's what I'm drawing there. Turns out that if this is charged up positively, so positive charge, then but it's an infinite plane, then the proton, the test charge that you put up here is going to be pushed directly up. So this will be the direction of the field. Now, that means then that there is no flux through the sides, because here's your dA. dA is this way for the side, and your E is this way. And so there is no flux out the sides. There's just flux out the top and the bottom, and actually the total the flux out the top is equal to the flux out the bottom, just because of symmetry arguments. There's just as much field going down, and the area is just is the same. So I'm going to call that area again. We could call it pi r squared, but I'm going to just call it A again. Okay, what's the charge enclosed? The charge enclosed is the only place where there is charge enclosed in this thing is right where it intersects the paper. The paper is what's charged, so it's this part that's charged. Let's call the top A1. We'll call the intersection of the paper and the can, that area, A2, and we'll call the bottom A3. So A3 is the bottom of the cylinder, A2 is where the can intersects the paper, and A1 is the top. They are all equal because that's a cylinder. A1 is equal to A2 is equal to A3. But I want to make a point here in this derivation. So what is the total charge enclosed? I can find that two ways. I can get the total charge enclosed by what is the net flux through this closed surface, this Gaussian surface? I can find that two ways. One way is to do the net charge enclosed over epsilon naught. Or I could use this method. I could just sum up all the E dot dAs. That's flux too. Okay, well the charge enclosed is just this charge, and so that's going to be sigma times A. You see how if I bring the A over here, that gives me Q? So sigma times A, but it's going to be sigma times A2. That's the A that I want to use, all over epsilon naught. That's an epsilon naught there. It's hard to read, but that's an epsilon naught. And that's equal to E dot dA. Now, the flux is out the top and the bottom. So the total flux out the top would be just the E there times the A, since the E and the A are in the same direction. E dot dA is the same direction. And you can pull the E out of the integral because the E is the same here, as here, as here, as here. The E is uniform at all points on here. And so because of that, I'll pull that out of the integral. And it looks like I get that the sigma A sub 2 over epsilon naught. Let me write that down here. Sigma A sub 2 over epsilon naught looks like it's going to be equal to the net flux, which is going to be E, pulled the E out of the integral, and then the only A's you have are this A, A1 plus A3. That's 2A. And so it looks like E will equal, if I make this 2A and make that just A, we can cancel out the A. And so it's just going to be sigma times 2 over, excuse me, it's going to be sigma over 2 epsilon naught. I'll write that again over here so it's more clear. The electric field then is sigma over 2 epsilon naught. Now notice something here. Notice that it's not dependent on how high above you are from the plane. There's no variables in here. It's just sigma, the surface charge density, and epsilon naught's just a constant. So the electric field above a plane is the same everywhere. And I just want to make a point about why that should be the case if you have an infinite plane. This is only if you have an infinite plane of charge, and that's because if that's your plane of charge and it's charged up uniformly, then the charge leaves and it goes parallel. That's the field. And see how that field strength, I'm trying to draw this in 3D here. These lines aren't getting closer or further from each other. They're not diverging. And so it doesn't look like the field is any stronger when you're close by. These are parallel lines. And so it doesn't look like the field converges or diverges, and so it never drops off as you go up. That's kind of interesting. All right, good luck. Bye.